Archie's not very impressed back there. But thank you, Palpatine. This video is going to be about electrical power. There are new equations. There are, two new equations we need to see in this video. But this will take us to the end of our circuits topic. So that's good news. Electrical power is a measurement we haven't discussed yet. We've been talking mostly about voltage, current, and resistance. Power is yet another measurement we can take in a circuit, and it's a combination of several of those other measurements. But let's first talk about what power is in general. You might remember this from our mechanics topics. Whether our power is measured electrically or mechanically, it's still the same idea. Power is the rate of doing work. Well, hold on. What's work? Remember, work is also known as energy. So I'm going to just use my mouse to point that out even more clearly. I'm color coding these words to make it, to link the ideas together. Energy and work are the same thing. So power measures how much work you're doing every second, or how much energy is being consumed every second. I'm going to use the words work and energy interchangeably because they are the same thing. So electrical power, in reality, we have electrical companies that are generating this electrical power, and then that power gets funneled through the electric lines, and they go through substations. You might notice if you look at the telephone poles outside, there are those giant gray cylinders. Those are transformers. Those transformers step the power down so that the last wire that goes to your house is 120 volts. That's the standard voltage for residential homes, except for the larger plugs like your dryers, clothes dryers, maybe larger like pool pumps. They may be 240 volts, but for the most part, we're dealing with 120 volts in our wall outlets, as I've said and explained to you in my problems many times. But anyway, let's look at the equation for how to solve for electrical power. So again, powers work over time. So let's just shorten that with the P for power, W for work, and T for time. Again, work is energy. If you want to use an E instead of a W for your variable, whatever. Units for power is the watt. Unit for work or energy is the joule. And the unit for time is the second. We've seen all these units before back in the mechanics topic, but I'm just showing you that it's the same topic, even though we're dealing with electrical power now. Here's the abbreviations for the watt, joule, and second. It can be confusing because the watt as a unit is a W, but work as a variable is also a W, so don't get confused. If you want to just write the whole word out every time, whether it's the unit or the equation, be my guest, but just be careful about that, please. So let's actually look at how to solve for power with electrical components, like I mentioned before: voltage, current, and resistance. Those are the three main measurements we're focusing on. How do they affect power? Well, here we go. Another definition of power, as long as it's the electrical form of power, is by combining the currents flowing through an object with its voltage. And by combining, I mean multiply. So our power can also be, our power equation for electrical power can be current I multiplied by voltage V. So that means a watt is also a coulomb per second multiplied by a joule per coulomb. These are the individual units for current and voltage. And if you want to just look at this for a moment, it's the C for coulomb is divided out over here. And so the watt winds up being a joule per second. That's exactly what it is if you look back to our first equation. A watt is a joule per second. Great. Now that's only one way to measure power, by taking the current and multiplying that by the voltage of a single component. If we remember Ohm's law, V equals IR, this is your row equation for any of those charts. You can get three different versions of this equation by substituting what I equals from Ohm's law, or then by substituting what V equals in Ohm's law. So just imagine a V equals IR if V is IR, you can replace this blue V with an I times an R, which makes this IIR. You can do that again for the I. I equals V divided by R. So if you replace this I with V divided by R, it becomes VV divided by R, or V squared divided by R. So all I'm saying is P equals IV is the easiest version of the power equation, but there are two others by mixing around Ohm's law. I squared R is another way to calculate power. V squared over R is yet a third way to calculate power. And this is great that we have three versions of the equation because all we need is two out of our three main circuit measurements in order to calculate power. Any two you have, one of the equations will do the job. All right, the last measurement of electrical components we need to discuss is electrical energy. Like we said before, energy is work. And if we just rearrange the power equation, again, power equation in its most basic form says power is work divided by time. Well, okay, just swing the variable around, multiply by time on both sides. You wind up with work equals time and power multiplied together. So I'll show you that here. Energy is power and time combined, power times time. So E equals PT again. You can replace this E with a W for work if you want. It's the same thing. Units, again, joule is a watt second. There's the abbreviations. And I'll also mention here that you guys don't pay your electric bills yet, but if you ever look at an electric bill, you are charged by energy, not by power, not by voltage, not by current. It's energy you're charged by, but you're not even charged in watt seconds. Oh, sorry, I have to replace this with a multiplication sign. I'll do that in the presentation, so you'll see it, even though in my video it's wrong. I apologize for that. It's a watt multiplied by a second. With your electric bills, you're charged in kilowatt hours, not kilowatts per hour, kilowatts multiplied by hours. So it's not watt seconds like the standard joule is, but it's some multiplication of it. I'm going to have you guys calculate the power that one of the electrical components in your home consumes. And I also like you to figure out how much money that costs every month to power. But I'm just going to say right now, the watt second equaling the joule is the standard way of measuring energy. But we're going to modify that to kilowatt hours for that activity. And I'll have explanations for how that works. Again, ignore this slash for division. This should be multiplication. I'm going to fix that. So when you look at the presentation yourself, if you want, it will be multiplication. Okay, but just like power, there are three versions of the energy equations. Here's the standard one. Energy equals power multiplied by time. Well, the power equation has three versions. It's either IV, it's I squared R, or it's V squared divided by R. Each time multiplied by T to make energy. So all three of these energy equations are the exact same thing as the power equations, just with a time multiplier for each of those three. It's that easy. So power and energy, very similar equations. You're just using time to multiply by power to make energy, or you're taking energy and dividing by time to get power. Of course, you want to make sure your units are correct, but we're going to modify them for our energy consumption activity, like I mentioned a minute ago. That's it for the power and energy equations. We can now add a fourth column to our VIR charts. I'll make one for power for a few problems going forward. And I also will mention here in this video that I don't have anywhere in text on the presentation. So good question for those of you who stuck around to the end. You know that voltage, current, and resistance all are treated differently, whether we're dealing with a series circuit or a parallel circuit. Well, good news for power is that it always adds up to a total regardless of what kind of circuit we're dealing with. So if I have 3 light bulbs and they're all in series and each light bulb is, say, 60 watts, that's 180 watts total power consumed in that circuit. Or I have those 3 60-watt light bulbs in parallel. Well, they'll have different amounts of voltages and currents running through them, But as long as they're each burning 60 watts, that's still a total of 180 watts total in that circuit. So P equations in a chart add up to a total, nice and easy. Thank you for watching. I look forward to seeing you guys in our Google Meet sessions. They're always posted on the outlines. So come on and drop by, especially if you need some help with any of our problems, whether they're the exit tickets or the document assignments. Next time you see me in a video like this, it'll be with our next topic of optics. But we're going to take a look at more circuits assignments before we jump into that. I wish you guys well. I'll see you next time, hopefully sooner in the Google Meets if you decide to come by. Bye-bye for now.